This video is for Physics of the Universe, Unit 1.2, Newton's Laws. Today's essential question is, what are action and reaction forces? And do action and reaction forces cancel out? Hello, baby birds. Today's video is on Newton's third law of motion. We're going to explore a principle that explains much of the movement that we see around us, especially when objects interact. Let's start with a real-world example. You and a friend are floating in inner tubes. When you reach out and push your friend's tube, what happens? You both glide away from each other in opposite directions. This isn't magic, it's physics. This interaction is a perfect example of Newton's third law of motion, which states, when one object exerts a force on another, the second object exerts an equal and opposite force on the first. Forces always come in pairs. They never exist in isolation. Our goal in this video is to understand how and why this happens, and how it plays out in everyday life. Let's dig into the concept of action and reaction forces. These are forces that act on two different objects, and they occur at exactly the same time. For example, when you push on your friend's inner tube, that's the action force. The reaction force is your friend's tube pushing back on you with equal strength, but in the opposite direction. Both tubes move, not because one is stronger, but because both forces are equal and opposite. This idea applies to many situations. When a hammer strikes a nail, for example, the nail pushes back on the hammer. When you lean on a wall, the wall pushes back. These are action-reaction pairs. Heads up for the following misconception. Many students think that only the object doing the pushing is responsible for the motion, but in reality, both objects apply force on each other at the same time, even if they don't move equally. Newton's third law says, for every action force, there is a reaction force that is equal in magnitude, meaning the number, and opposite in direction. This law tells us something very important. Forces do not exist by themselves. They come in matched pairs, and they occur simultaneously. That means that as soon as you exert a force on something, that something pushes right back. It doesn't wait, it doesn't hesitate. The forces are automatic and mutual. Even when you can't feel it, like when the earth pulls you down and you pull the earth up, the law still applies. You can find examples of Newton's third law everywhere. If you were to set a book on the desk, it pushes down with its weight. The desk responds with an equal force upward, which prevents the book from falling through. That upward force is the desk's reaction. Lean against the wall, for example. The wall pushes back. Otherwise, you'd fall into it. Swim across a pool. Your arms push water backward, and the water pushes you forward. Every time something moves as a result of a push or a pull, you can be sure that an equal and opposite force is being exerted back. Birds take advantage of Newton's third law every time they fly. As a bird flaps its wings, it pushes air down. This is the action force. The air pushes back upward on the wings with equal force, making it the reaction force. That upward push is called lift in the context of birds. And the lift, is what lets the birds rise and stay in the air. The bird doesn't rise because it's flapping alone. It rises because the air reacts. Without the air pushing back, flight wouldn't happen. The same principle applies to rockets. When a rocket burns fuel, it produces hot gas, or lots of hot gases, I should say, that are expelled downward out of the engine. That downward push is the action force. The gases respond by pushing the rocket upward. That's the reaction force. That equal and opposite force is what lifts the rocket. Newton's third law explains every rocket launch, every space shuttle, even booster stage. Everything that goes up does so because of the matching downward force. Here's a helpful trick to identify action-reaction pairs. Step 1. Identify the force. Let's say the bird's wings push down on the air. Step 2. Switch the order of the objects. That becomes the air pushes on the bird's wings. Step 3. Flip the direction. The air pushes up instead of down. This logic applies everywhere. Nail and hammer, swimmer and water, and inner tubes in a pool. Now, another misconception alert. Some students think action and reaction forces must always involve motion, but that is not true. Even stationary objects experience these force pairs. If you sit in a chair, gravity pulls you down, and the chair pushes up. No motion required. Let's return to our inner tube example. Imagine you are the smaller person and you push a heavier friend. You both move, but you, as the smaller person, shoot off faster. Why? Remember Newton's second law, F is equal to ma, tells us that the same force causes different accelerations based on mass. If you push with 60 newtons of force, the force your friend feels is 60 newtons. And you also feel 60 newtons back, action-reaction forces. But since you have less mass, your acceleration is greater. Equal forces do not mean equal motion because mass changes the outcome. Another misconception alert. Many students think equal forces must cause equal motion. But what we're saying, the accelerations will differ if the masses are different, according to F is equal to ma. So let's solve this particular calculation on screen here. Two kids in an inner tube, or in inner tubes, plural. The smaller one weighs 40 kilograms. The larger one weighs 80 kilograms. The smaller child pushes with 60 newtons of force. Let's use Newton's second law here. But let's rearrange it to solve for acceleration. So now it looks like A is equal to F over m. We can calculate the acceleration of the 40 kilogram boy. That's going to be a negative 60 newtons divided by 40 kilograms, which is equal to negative 1.5 meters per second squared. The negative sign here means that it's moving or accelerating in the opposite direction. The acceleration of the 80 kilogram boy, again, acceleration is equal to positive 60 newtons divided by 80 kilograms, which comes out to be a positive 0.75 meters per second squared. So the lighter boy accelerates twice as fast in the opposite direction. The equal and opposite forces cause unequal motion due to these differences in mass. Now, this is a big misconception. If forces are equal and opposite, don't they cancel out? The answer is no, because they act on different objects. Action and reaction forces don't cancel because they never act on the same thing. Take a hammer and a nail. The hammer exerts a force on the nail, and the nail exerts a force on the hammer. But the nail accelerates into the wood while the hammer slows down. That's not cancellation, it's interaction. So don't say the forces cancel. It's better to say that forces balance, and only when they act on the same object. Let's think about gravity. When you drop a pen, Earth pulls it down. We all know that. But according to Newton's third law, the pen also pulls up on Earth with the exact same force. So why doesn't Earth move? To be honest, it does. Just very, very little. Earth is so massive that its acceleration is so close to zero, we can't tell the difference. Still, the force is real. This also explains why a pen stops when it hits the floor. The ground pushes up with a normal force equal to the pen's weight, stopping its motion. Newton's third law applies to electric forces as well. If we place two like charges near each other, say two positive charges, they repel. One pushes on the other, and the second pushes back with the same force. If the charges are opposite, however, they attract with equal force. In both of these cases, the electrostatic force allows Newton's third law. Equal in size, opposite in direction. Friction is another example. When you drag a heavy box, the box pushes against the floor. The floor pushes back with an equal force in the opposite direction, which we call friction. This is what slows the box down. And sometimes the box can even scratch the floor because it exerts a force on it. This also explains how walking works. You push backward on the ground, and the ground pushes you forward. So to wrap it all up, Newton's third law tells us that every force comes with a partner. They're always equal in magnitude and opposite in direction. They always act on different objects, which means they never cancel. They interact. We see this law at work in walking, swimming, flying, rockets, and yes, even two people pushing off in inner tubes. If you remember one thing from this video, remember this. Every push or pull that you apply to something, it pushes or pulls back on you with the exact same strength. That's the beauty of Newton's third law. At this point, you should be able to generate a full and appropriate response to today's essential question. What are action and reaction forces? And do action and reaction forces cancel out?